Rather than waiting for anybody else to show up, we need to start. It's 12:31. So I'm going to try to finish state space models today. There will be more things in there they are, the Landeliers, as they say, and more. Okay. So what I was going to say, we're going to try to finish state space models, but there is lots of stuff in the nodes that I don't think I will cover, so that you don't get a headache, and also we can discuss more topics. So what I want to do today is something sort of elementary and in some ways implied in the things we have seen before. So last lecture we derived the Kalman filter equations for linear dynamical systems from scratch, basically. We looked at the equations. We said there is this independence relations, and playing with probability laws, we derived the Kalman filter equation. So what I want to do is, I want to show you that, in essence, everything we learned about message passing, when we apply that to linear dynamical systems, actually will give us directly the Kalman filter equations, and can be generalized as well. So I'm going to do this, highlight basically some of the derivations, the way they go. They are not trivial, so in some sense you're doing extra effort using message passing, but at the expense basically of having an algorithm that is very general. Okay? And considering that this is a course on probabilistic graphical models, sort of we have to do this. I will suggest actually that you guys, as part of the homework 5 maybe, you do some of the analytical calculations that I will discuss today, because there is much to learn, and they are not very difficult, but in essence if you do them, you have a good sense of both message passing, but also of dealing with the Kalman filter type of equations. All right. So let me review for you the factor graph that corresponds to the state space model of interest. The only thing that is different here that I want to remind you is that the way that we define these factor nodes, we incorporated both the transition model P of Zn to Zn, from Zn minus 1 to Zn, but also the observation model. So keep that in mind. So it looks like a chain thing, but in reality we have accounted for both probabilities in one factor. And similarly for the first factor here, H, is the probability of the initial state and the observation model in the initial state. All right, so the message passing, and you don't have to remember any equations because really it is graphical. So let's concentrate on this equation. We only look at messages that factors pass to nodes, all right? Nodes don't actually do anything in this graph. So the message from Fn to Zn is the factor itself, all right, which connects the variables Zn minus 1 and Zn, times the message that the factor Zn minus 1 that is somewhere there passes to node Zn minus 1. All right, makes sense. Whatever comes in plus the factor, and then you integrate Zn minus 1 out, and you get Zn. Now, if this, the variables are continuous, as will be in our problem, that summation will be an integral, okay? The first equation basically says that the message that the node passes to a factor is the same as the message the previous factor passes to this node. So in essence, it emphasizes that we are just happy enough to only work with messages from factors to nodes. We don't need to bother from messages from nodes to factors. All right? So this is the forward message passing, and we call this the alpha message. Okay? And we discuss sort of two different notations. One that the alpha message corresponding to this, it was the posterior of Zn given all the data to time n. And I think another notation was and a normalized posterior effectively. So if you don't want to get confused with the notation, effectively you can write that this is proportional to what you see on the right-hand side. So when you compute the right-hand side, then you normalize it and you get a distribution. So one way or another, it doesn't really matter if you see different notations. Okay, so this is the forward messages, and I also want to show you the same schematic basically, the backward messages from the root to node H to the left. So the message passing is basically identical to the forward things, but it goes backward. So the message from the factor Fn, let's see, the message from Fn plus 1 to node Zn, all right? So again, we're looking at messages from factors to nodes. So this message here, okay, is this factor times the message that the factor Fn plus 2 sends to node Zn plus 1, which is this. And obviously this message is the same as that message, right? So again, this message is this factor times this message where we integrate out Zn plus 1. And obviously you can see that this proceeds backwards because we require this message to the right to compute this message to the left, and the integration is to the variables to the right, which is in this case Zn plus 1. And we call this the beta message. Okay, so the beta messages go backwards, the alpha messages go forward. So what I'm going to do is I'm going to play with these equations and derive for you the Kalman filter equations. And it looks sort of a massive algebraic calculation, but I recommend that you do it, because not only you'll be happy that you discover the Kalman filter equations from a completely different way from the way Kalman derived them, which is actually different from the one we already have done in the earlier lecture, but there is much to learn both from message passing and playing with Gaussians, conditionals, marginalization, things like that. Okay, so I am going to use first the forward equation that defines the alpha messages. And again, as I told you, if you don't want to worry what the normalization constant here is or what alpha is, you don't need to bother, okay? You just say this is proportional to that, and you normalize, and whatever you get, that will be the alpha message. But here I'm writing it in a precise form, okay, where this message is the posterior of Zn given all the data, the observations up to time n, okay? And this coefficient is Cn, scalar, is basically the probability of xn given x1 to xn minus 1, okay? Again, if you write this, rather than having this filtering distribution, you have the joint distribution of Zn, comma x1 to xn, you're not going to get that Cn, okay? But more or less the equations are the same. All right, so you look at these equations, right? And obviously we're going to make that summation an integral, and we want to get a methodology to derive an inference algorithm that is linear in the length of the chain. We need sort of to take advantage of the structure of this equation in a way that when we plug in here whatever distribution this alpha message is, we would like to get the same sort of distribution for the message alpha Gn. And in some sense, if this belongs to some family of distributions, we would like the only thing to have to do when we apply this equation to update the parameters of this distribution to get the distribution alpha of Gn. Right, so if this is a Gaussian, for example, right? It would be great if somehow this is also a Gaussian, and the only thing we have to do is update the mean and the variance of the previous distribution. Okay? Now this goes beyond Gaussians, right? And this, will fit perfectly with any distribution from the exponential family. But today we will discuss basically this, the Gaussian distributions. Okay. Now, if so, we're going to take a model, this linear Gaussian state space model, where basically both the probability of Zn given Zn minus 1 and the probability of Xn given Zn are Gaussians, and then at the end of the day, basically, all the distributions we're going to get will be Gaussians. So the joint distribution of all latent variables will be a multivariate Gaussian, and we have seen actually this problem, and I think you have done it, you have sort of done a homework problem with this, but we will see a different perspective here. So let me give you the results, summary of the results. If you apply for a Gaussian linear system the forward passing message equations, you get the identical equations corresponding to the Kalman filter. Okay? If you apply the backwards recursions, so you know this is the beta message, you get the Kalman-Smoother equations that I think, if I remember, we didn't have time to cover in last lecture. I may be wrong, but we stopped there. But you can imagine that similar to the beta message, right? These Kalman-Smoother equations basically will give us the posterior of the hidden variables given all the data from 1 to capital T. Okay? That's why these equations are called smoothing equations. So this is nice, right? Forward gives me the Kalman filter, backward gives me the smoothing equations, and actually if you do the forward and the backward equations, you can get the sufficient statistics for the hidden variables that are needed to compute the parameters via expectation maximization. You remember that? When we did the HMM? So we will actually try to, at least I'll highlight for you the equations. If you don't need to compute the parameters and they're fixed, right, depending on what your interest is, if you want the predictive distributions, the forward equations will do it. If you want the smoothing, the backward will do it. If you're going to do the EM algorithm, you have to basically do both alpha and beta messages. I'm going to use the notation from Bishop's book actually to simplify the notation, so the U variables that we had, but effectively they were nothing else but a constant term in the mean of these distributions. I omitted here, but actually you can show, you can take the final results, and with a trivial trick you can discover the, you know, the modified equations when there is an extra term on the means here. But right now, concentrate on the way these two equations look like, right? So A and gamma will define the transition model for the states, and this is the observation model with matrices here, sigma and C and sigma. Remember this because I will forget and we will be lost with the algebra, okay? So A and gamma, C and sigma. We're supposed to start from some initial state, and so the initial state is going to be given also as a Gaussian. I mean, you can see actually later on, maybe in the slides, if we have time, and I remember I will let you know, if this is somehow not a Gaussian mixture, then you get different equations from Kalman filtering, right? So this is not a joke. Basically, you need to start with a Gaussian, otherwise you will get in trouble. So these equations, basically, if you don't want them written in terms of distributions, you know, this is how the equations look like. They're all linear, right? That's why we call this a linear dynamical system. So later on, we will actually, if I don't have time, you will have to read it, right? But we can extend this where, for example, here, rather than having some linear function of Zn minus 1, maybe we can put some function f of Zn minus 1, or here some function g of Zn, okay? But right now, everything is linear and everything is Gaussian. So lots of parameters, right? So from the dynamics, basically we have A and gamma. From the observation, we have C and sigma, and from the initial model, we have mu0 and p0. So really, if you want to complete the problem and do expectation maximization, you need to basically calculate all these parameters from observations, okay? And in some sense, this is something, at least in engineering books, you will never see. Nobody bothers to tell you how you compute these parameters, but really the algorithm here is just a simple application of EM the same way we work with hidden Markov models. Okay. All right. So let's derive the forgot equations for these alpha messages, and somehow let's discover that these equations are really the Kalman filter equations. So what I'm going to do is, since this is a forgot algorithm, I'm going to denote, so everything is a Gaussian, so I am going to denote this for the alpha message, corresponding to state Gn. I'm going to denote the mean and the variance as mu n and Vn. And the idea here will be that I am going to start with a method Gn minus 1. So I'm going to know this mu n minus 1 and Vn minus 1. And then somehow using this forgot message passing equation, I should be able to update mu n minus 1 and Vn minus 1 to mu n and Vn. Okay? Nothing major. So basically what I have done is I took this equation and I expanded it by plugging in all the terms. So Cn, remember again, is really not necessarily, sometimes confusing, but to make this an equal sign here, you need that. So this is the message times this Gaussian, okay? The observation model is here. The method n minus 1 is there, so we suppose we know this. And this is the transition model, looks like that, and the n minus 1 is integrated out. Okay? So again, the problem is, given this, because we will do it this as we move forward, we want to compute that. Okay? And I suppose in the process, if we want to have these equations properly normalized, we will need to update these coefficients Cn as well. All right. I am going to try to highlight as much as I can. All right. The rest, I really suggest that you do it as a homework. Okay. So every derivation that there is on the slides, practically the proof is in the slides, but I want you not just copy these formulas, actually go and derive them, because you will learn about manipulating Gaussians, about the Woodbury identity, marginalizations, conditionals, Bayes' rule, everything is there. How can you go wrong? Okay? So, what I'm going to do is first, I'm going to look at this integral. Is this integral a Gaussian, and why? The whole integral. And if it is a Gaussian, from where is that magic of coming to be a Gaussian? Why it's a Gaussian? This integral. What do I have in this integral? I have the product of two Gaussians, but the mean of one of them, all right, is linear on the other variable. So it's really what I have is like having a probability, let's say, of y given x, all right, that is linear in x, times the probability of x. And what I'm asking is to find the probability of y where I integrate x out. Right? Because I want Zn minus 1 out, right? So basically, this is like having the joint distribution of two Gaussians and you want to marginalize, okay? So the idea is, this is the formula that I cut and pasted, not everywhere, but you guys will do the algebra and you will learn it better than me. So here is like having convex distribution Px, all right? This is given, all right? Convex P of y given x, all right? And you notice the mean is linear in x, which is Zn minus 1. You see that? There's no b here. And sigma y, of course, is gamma. So from manipulation of this for linear Gaussian models, P of y comes to be this nice distribution that has mean that you see here, and it has variance that looks like that. Those formulas, you don't need to prove them. You prove them once in your life, and you work with them, okay? Be sure when you see them the first time in a textbook, you derive them, because a little mistake in the textbook will mess up the rest of your lives. I mean, I can easily see that because I've seen those mistakes in textbooks, all right, in the most common formulas. So, so P of y is given like that, right? So this integral, I can write it as a Gaussian that looks like that, and it comes up that the mean is a times mu n minus 1, and the variance is Pn minus 1, where the variance is written by this, is coming up from this nice formula, okay? You don't have to believe me, because this is the variance, you plug it in, and that's what you get. Okay? All right. So, obviously I'm putting n minus 1 here, everything, because, you know, you notice all the variables here refer to time n minus 1. So we call this intermediate matrix Pn minus 1. Okay, now look at this formula. So this integral, it comes out to be a Gaussian in Zn. So this integral is a Gaussian in Cn. And what is this integral? Is a Gaussian in Xn that has a mean that's linear function of Zn. So what can we do? We need to do two things, right? We need basically to compute the posterior of this. So here is not marginalization. What we need to do is sort of from P of x given y, go to P of y given x, all right? And this coefficient sigma n is really P of x, is the normalization factor, okay? So, so here is what you need. You know P of x, I'm using this generic notation, and P of y of x, and we need to invert this, and we need to compute P of x given y, and that is given by this nice formula with this mean and this variance, all right? And actually the results I have written down, they don't use this variance as you see it here, all right? What they use is, they use the Woodbury identity, where if you compute this, all right, you can simplify to actually Pn minus 1 minus Kn times Cpn minus 1, where Kn comes to this. And I know you forgot, but this Kn, it is identical to what we derived in the last lecture, which is the Kalman gain matrix. Okay? And this coefficient sigma n, okay, which is basically this marginal of xn, it's also a Gaussian that comes like that, okay? Again, we're less interested on sigma n, but if we want to make the equation to have an equal sign, all right, it has to look like that. This is the normalization factor. And look at this equation on so let me just remind you what we computed, right? What we computed is the mean of the variance of the alpha message, and the alpha message is the filtering distribution of Zn. And the filtering distribution is the probability of Zn given the data x1 to x little n. Okay? So, look, so this is the mean, all right? This is the mean for this filtering distribution. Can you put me some physical meaning to this equation? So that if you have some physical meaning, then you can write the equation from intuition rather than algebra. So what is a times mu n minus 1? So you take basically the filtering distribution at n minus 1, and you push forward the mean with the transition matrix A. You see that? Okay? So that's what it is. And now we have this gain matrix times some error, and that error is the observation that so suddenly you see data, that's your observation at time n, all right? And what is CA mu n minus 1? You just told me that A mu n minus 1 is this transition is pushing forward the previous mean with the transition matrix A. So what is C times A mu n minus 1? It's the mean observation that you will have, and this is really the error that you do, and effectively you have a learning matrix, which is this Kalman gain matrix, right? So K times this error plus the first term gives you the new updated mean, and that's the right answer. Okay? Of course, you know, this is easy to remember, but you will not remember that actually the exact learning matrix, this gain matrix, is given by anything like that. But you know what? At the end of the day, as we know for stochastic optimization, it doesn't really matter. In other words, if you put something else and you start iterating, you will get the right answers anyways. Okay? But we want to do things exactly, and this is how the mean looks, how the variance, and how CN looks. You need to start the algorithm, and so if you take the message passing on the first step, the first message basically requires the initial state, the probability of Z1 times the first measurement that you do. So this is our first P of Z1. This is the emission of X1, okay? So if you plug in, actually following practically the same algebra as for message passing, it's simpler the algebra because you don't have any integral or anything like that. Here is mu1, and here is v1, and the constant v1 is given like that, okay? So you have a way to start the algorithm, and then you use the update formulas, and that's the Kalman filter equations, and done. Okay, in a few minutes we'll basically finish with the Kalman filter equations using ideas of message passing. Just to give you sort of a graphical representation of the way that you compute these filtering distributions. So I think this is how we derived these things last week. So this is the filtering distribution at n minus 1. Then you use the transition model basically defined by this probability of Zn given Zn minus 1. So you update basically the state Zn still using the measurements from x1 to xn minus 1. So this is like a diffusion model, and the variance of this dictates basically a distribution that is much wider in support than this filtering state at n minus 1. And then effectively to get the filtering state at time n, you basically have to multiply with the observation model, okay, that looks like this, and eventually this very broad push forward, if you like, or one-step predictive distribution now is modified to give you this blue distribution that is the filtering state at time n. So basically, again, one-step prediction, ahead, and then you collect the measurement xn and you update with this model, probability of xn given Zn, and you get the right result. All right. So now we have to discuss the backward message passing. I'm going to do this fast because basically the questions look the same. Okay. You will only be interested on this backward passing for getting this smoothing equations that I don't think I covered, or maybe it was in the last 2 seconds on the previous lecture. So we need to get the smoothing distributions, but also I remind you that we have defined these gamma messages, okay, as the product of the messages coming at each node. So the product of alpha and beta, and these gamma messages define the sufficient statistics that we need on the EM algorithm, okay? And we will briefly discuss the EM algorithm as well today. All right, so the bit update looks like that. We basically have to go backwards. We have to start with the message at n plus 1 to compute the message at n. I have defined exactly the messages here so that this is equality, including the constant that I have. And again, you can look back on the previous lecture that I had this equation both in normalized and normalized forms, okay? This is precise like that. And again, what's the meaning of the beta message is the probability of having observations xn plus 1 to x capital N, given that I start at state Zn at some value, okay? So that's the beta message. All right. I am not going to give you the algebra, but basically what you need to do is, since everything is a Gaussian, let me see, we're going to assume that this beta message is it given anywhere? All right, so we have this, okay, we know that, we have that, we know that. We know the updates from the alpha messages, we know the CN. So obviously, what I have is, rather than giving you the beta messages, and actually, if it is not in the slides, maybe that's an excellent homework to derive explicitly the beta message and show that that's the smoothing Kalman filtering equations. Okay, so basically what I have is the combined message of alpha and beta in the derivation, but if you only use this to compute this beta messages, then you get this the smoothing distributions. So what I have here is I define the gamma to be a Gaussian with mean this mu n hat and v n hat, and you can show by effectively what you need to do is multiply this with an alpha message, all right? So you can get the gamma message on the left, and then plug in everything you know on the right. Everything is a Gaussian, and here is the final answer. The mean and the variance for the gamma message is the mean and the variance that we computed for the alpha messages times these are the mean and the variance one step ahead, right? Because these are backwards equations, minus alpha mu n minus Pn that we derive it, and this matrix Jn here is given Vn times A plus pose Pn minus 1. Okay? So a very nice equation, and I think these are the equations actually for the Kalman smoothing algorithm. If you see in the notes, basically, you will immediately recognize what equations you need to show coming out of this for smoothing. All right. To apply these equations that give you the gamma message, obviously, you have first to run the forward message passing to get mu and v, and then go backwards to calculate gamma. Okay? All right? So you have to do those in sequence. Now, there is one more distribution that you need to get on the EM algorithm. You remember that? You remember this weird distribution? The joint distribution of Gn minus 1 and Gn that comes? We did this when we did apply the hidden Markov, the EM algorithm for the HMM model. Okay? So we will need to compute this joint distribution posterior of Gn minus 1 and Gn. All right? And there are multiple ways of doing it. And here obviously the most trivial way to do it is to take the message that arrives on node n minus 1, an alpha message, the message that arrives on node beta from the right, and then multiply with the transition model and the observation model, and that will give you this distribution. So when you plug in all the distributions, what it comes out is that the joint distribution of Cn minus and Cn is mu n minus 1 and mu n. I remind you, these are the means of the gamma messages, okay? And the covariance is Jn minus 1 times this variance of the gamma message, and the J matrix, somewhere I wrote it, is given by this. Okay? So nobody said that equations are easy, right? But if you think of writing a computer program that implements this, it's basically, once you put the analytical expressions, the whole algorithm is basically 10 lines. And I've literally seen, I mean, if you search on the web and you download the Kalman filter algorithm, it's 10 lines. Because the MATLAB knows how to manipulate Gaussians, and you don't have to do much. You give the exact expressions, and the rest is history. Okay? All right. So I need to tell you a little bit on how we're going to get all these parameters now that we got the sufficient statistics for, we got the sufficient statistics for from these gamma messages. So I remind you what we need to do in the, what's the EM algorithm? Can somebody remind me? So what are we supposed to do? Yeah, so what do we do? We take, well, so the expectation of what? The joint log likelihood. So we will take basically the joint likelihood of observations and hidden variables, because that's a very easy distribution, right? Gaussian, basically easy to write down, especially the log. And because we don't know z, we will take the expectation of that with respect to the posterior of the z variables. So that will be the E step, to do that computation with all the parameters fixed at values theta all. And then once we compute that, so that will require the sufficient statistics, because that expectation with respect to the posterior of z, right, will require the mean of z and, these z variables that we saw before. So that's part of the E step. And in the M step, basically, we are going to take derivatives with respect to the theta parameters, and we will provide update. And the theta parameters here are sort of massive because we have 1, 2, 3, 4, 5 matrices and one vector. Okay. The nice thing is you will see that the equations actually decouple, and almost in a trivial way, they look like updating a lot of these matrices, like the covariances, like gamma and sigma. You will see that it looks almost like working with estimating the mean and the variance of multivariate Gaussian. So basically doing MLE estimate for a multivariate Gaussian. And as you know, when you do MLE, you basically get the sample mean and the sample variance coming out of this. Okay, so this is the sufficient statistics that you will need, right? The expectation of Zn, we already computed it. We will need remember this join things? We need the expectation of Zn, Zn minus 1 transpose. So you can, since you know the distribution of the join distribution of Zn and Zn minus 1, this will be the variance of that distribution minus mu transpose, and then of course you will need the expectation of Zn, Zn transpose that is given like that, and all of these quantities we just computed. All right, so this can be sort of in the E step. So the log likelihood, it's trivial because you have the initial observation model, the initial state model, and then the transition and the measurement, and these are Gaussians. So when you take logs, actually they're simplified in a trivial matter. So this is what we need to compute. We need to take the joint log likelihood and take the expectation with respect to parameters. The expectation with respect to the z variables, keeping the parameters fixed. So let's do sort of a trivial application of this to computing mu0 and t0. I remind you those are the mean and the variance for the initial state. Okay, so basically in that expectation of the joint log likelihood, only this term will give me contributions that involve mu0 and t0. And really, estimating mu0 and t0 is like an MLE for a multivariate Gaussian, right? It's identical, okay? So when you write, you expand this, this is what you get, right? The only difference from doing MLE of multivariate Gaussian, here there is an expectation with respect to the z variables. So you notice the expectation will involve expectation of z1 transpose z1 and also expectation of z1. Those are the sufficient statistics that I showed you before. So z1, expectation of z1 and z1 transpose. So you have those answers. And so when, these are the statistics you need to compute, okay? And in the M step, where is the maximization with respect to mu0 and p0 would be the same thing as a multivariate Gaussian, and basically these are the results that you get, okay? So the updates of the mean and the variance are given basically actually in terms of the sufficient statistics, because this is sort of expected result here, okay? These are, again, like the sample mean, right? And this is like the sample variance. If you write the expectations in terms of samples. Okay, very fast, if you want to calculate, for example, A and gamma, okay? You need to expand this term. So if you expand it, you will get something like this, all right? And you compute your sufficient statistics, then you take derivatives with respect to A and gamma. Again, it looks identical to a multivariate Gaussian, and the updates of A and gamma in the M step look like this. Really, the only thing you need to compute, again, is the sufficient statistics, okay? And the sufficient statistics for A and gamma, obviously they involve all the sufficient statistics over all little f's, all right? So you don't have, in this case, all right? Well, I suppose in the previous case, for the initial state, you didn't have the summations, but here basically these are the summations that you need to make this figure. And similarly, for this calculation of sigma, of C and sigma, that they come in the observation model, again, the sufficient statistics look like this, okay? And actually, you can see immediately why we had called Zn to be sort of the, what's the name we gave to Zn? I forgot. Remind me. Say the word. I forgot. I'm tired. I'm jet lagged, I am justified, What's the word? Responsibility. Right, the responsibility. Okay. Similar the concept to the responsibility, because you're computing Cn, you take all the observations, but you assign a posterior probability to each of them, right? In estimating the updates of C and sigma. If you want to, to do a math estimate, basically the only thing you need to do is when you go in and what is the equation? When you go and you compute this expectation of the joint log likelihood, the only thing you have to do is, right, go and put some log of the prior probability there as well, and the rest is sort of, it will change a little bit in the derivative, so you get some extra terms that act as regularizers basically, but getting the math estimate is sort of trivial. Now again, these things, they look like homework type of problems, but as you can see, homework problems, there were lots of progress on understanding how these algorithms work. There were things done in the last 15, 20 years. So this is a nice reference that contains this sort of calculations. Okay. I'm losing my audience. What is happening today? It's like I'm turning my back for 2 minutes and then everybody's gone. Not a good sign. All right. If let me say the following thing, right? If you try to play with this message passing, and there are references, I don't have them here, but if you search, you will find ways of doing this. But let's say that somehow you're not happy with messages that are Gaussians, right? I mean, I can, maybe your noise model is not Gaussian, maybe your initial state is not Gaussian. So how do you use this equation, let's say, when this is a Gaussian mixture, okay? Now, if this is a Gaussian mixture, right, and there's a typo here, okay, xn given zn. So if you start, let's say, with a message of AZ1 that is a Gaussian mixture, then A of Z2 will be a Gaussian mixture with k squared components. AZ3 would be a Gaussian mixture with k cubed components. So basically, you're going to get a combinatorial explosion in components of these messages. So the only way that you can pursue sort of a non-Gaussian representation using mixtures here will be to actually do the calculations with these mixtures, but before you update and you go to the next step, project them back to k components. So you do calculations with k square components, but then approximate this again with k components. And there is work, if I remember, out of the group at MIT that had done this type of calculations maybe 10 years ago or so. So basically, yes, Gaussians make these update formulas analytical, but if you want to use anything that's non-Gaussian, you are in new territories, and you have to be very careful how you do it. Okay, it doesn't mean it cannot be done, but it means it's not going to be as easy to compute as the Gaussian models. All right. All right. Now, this is a topic very much related with this type of extensions when the messages are non-Gaussian. How do you actually, are there any other methods, okay? And one of the methods that allows you to do messages that are non-Gaussian is to use particle representation of the messages. So you can think now basically having the messages represented in terms of samples, all right? And I know in the fall I gave at least 3 or 4 lectures on the topics. I'm not quite sure how mature will be for us to discuss a lot of details, right? So I'm going to try to spend maybe 10 minutes, okay? Because these methods are extremely powerful. Like, for example, in robotics, in tracking, everything is using particle methods because Gaussian mixtures don't work. Gaussians are the wrong approximation. So the only way out is some approximation method or using these particle filters. Okay? Now I know about a third of the class attended my lectures in the fall, but I also trust that they remember nothing. Okay? Right? You see? They remember absolutely nothing. So I'm not going to, let me jump, okay? So I am not going to tell you everything. All right, so let me discuss sort of this prediction and updates of the states that we use basically for the Kalman filter equations of the previous lectures. And what I have here is, rather than updating one state at a time, I'm updating, so in this case, on this step 1 that says prediction, I have data from 1 to n minus 1, all right? And I'm updating all the states, including now state n. And the idea here of the prediction step is that I already have this distribution of the joint of z's from 1 to n minus 1 given x1 n minus 1. So this prediction one step ahead, only involves this dynamics, the probability of Zn given Zn minus 1. Okay? Right, so again, for the filtering equation, the prediction step involves only the variable Zn. Here, just because I copied this equation for a much more general sort of type of calculations, I demonstrate this where we keep the posterior of all these variables. Okay? So this is the prediction for one step ahead that we have seen. And as we discussed even today, if you want now, if you observe also the data point xn, and you want to update the posterior of all the z's up to n, then effectively what you need to do is take this distribution and multiply it with the observation model xn given Zn. So what are the particle net methods? So if you make all of this Gaussian, then you get these Kalman filter equations, okay? Because here I don't have all my observations, only it's up to n, okay? So if you get the Kalman filter equations for these four good alpha messages that we discussed. So the idea of these particle methods are, as you move forward in time, to represent these distributions with samples, with delta functions, okay? And somehow, rather than resampling the distributions as you go from one step to another, update basically the weights of these delta functions as you go from n minus 1 to n. All right? So the idea here is that you have delta functions, but so when you do classical Monte Carlo, the weight is the same. Here we're going to have weighted samples to express these distributions. And if you write these distributions in terms of samples, you can actually in principle represent any sort of distributions. It can be anything, all right? Anything. Now if the distribution is very complex, you will need more samples, but this idea is here. It comes out that if you take the samples and sort of you update our weights from one step to another, the algorithm has the complexity that depends linearly on the number of the samples, not on the little n. So in principle, you can keep doing this forever. You can compute Pascal the filtering distribution from time 1 to infinity, even though there would be degeneracy issues and other things that we have no time to discuss. Okay? So let me give you basically, I'm going to go directly on the picture, okay? Since this is a little bit off from the emphasis of what we have. So, so what I have here is, imagine that the time n, we know the filtering distribution, and I write this filtering distribution in terms of these particles. So these are delta functions that are, centered basically on these particles, capital of Z, n, okay? And these are weights, okay? And the weights actually, when I represent, these are the particles at different locations, and to indicate which weights are bigger, basically you see these circles are bigger, okay? All right, so to be able to move forward these particles and compute the filtering distribution at time n plus 1, you remember I need to do two things. First, I need to move those forwards with this dynamical model, and then I need to apply the observation, the emission probability as P of x given Z. So the way you do it is, assuming that you have this particle distribution, you take this update equation that I had before, all right, and you apply, you remember the update equation? Somewhere I had an update equation. What is it? Here. This is the prediction for one step ahead. The only thing you have to do is take this approximation in terms of particles and then multiply this with the dynamical model of P of Zn given Zn minus 1. So basically this is what I have done here. All right, I compute the posterior of Cn plus 1, still given, with only the date up to time n. So this will require this posterior of Zn plus 1 given Zn, And then because here I have these delta functions, this posterior will have to be calculated given its particle. I don't know if you can see what you actually get from there is sort of a Gaussian mixture. All right, you get a Gaussian mixture distribution, okay? And because we don't like Gaussian mixtures, what you can do is you can resample this, all right? You can resample this and you resample it so that all the new samples basically have equal weights, the way you do with Monte Carlo, and these little squares here, little circles of equal radius basically are the new samples that give you this one step ahead predictive distribution. Okay? So again, I took my filtering distribution at time n, and I now do one step ahead prediction with resampling, and I get these little circles, okay? And what remains is to actually multiply this distribution with the observation model, which is P of x given z, and if you do that, because you have these delta functions, the new distribution will be basically P of x given each of these particles times these delta functions that you computed there. So you can see the new filtering distribution, the location of the particles hasn't changed, but the weights have changed because the weights now are dictated by the observation model of P of x given z. I know there is too much there to get, but I need to tell you about this because sort of these methods are the methods that are used in practice. This is how you're going to implement, let's say, Gaussian models, maybe even nonlinear models, or if you have non-Gaussian noise, these methods work, and they are sort of the standard methods for implementing these update equations in many areas. All right, in many areas. Okay. I'm actually, for good or bad reasons, I have committed to give I don't know how many lectures this summer in another university on sort of this type of methods. So if you are interested, I will try to sort of prepare specific notes from scratch, basically, for this particle filter method, maybe by mid-June or so. Okay, so otherwise you can look at the notes from the course last semester that contains more information. Any questions on this, at least in spirit, what they are? I mean, the whole idea is represent the distributions, these filtering distributions in terms of samples, right? And a distribution in terms of samples is a bunch of delta functions, right? You just need, depending how you do the sampling, to know if the weights are equal or they are different, okay? And so in this case, you start with, so when you see some of the circles bigger than others, the weights differing, but if you resample from this, you notice like this sample that has big weight, as you resample, it gives you two children, right? That's the idea, because it has more weight, okay? But it's now the new samples, all of them have now equal weight, okay? And then this is your observation model. So obviously these samples, for example, here, when you pass them through this observation model, we have bigger weights. And again, here we have bigger weights and they are small. And so this is sort of a very powerful way to do filtering, to do smoothing, to do lots of different type of things. And they're the standard methods, as I said, in robotics, in any sort of dynamical problems, not only robotics, actually, anything. All right. We have a few minutes left, so let me tell you how, so we can finish this topic, how you extend these ideas when the model is not linear, all right? So, so we had two linear models, right? Both the dynamics, it was for the Z, you remember Zn equal A, Zn minus 1 plus noise. Let's say that the relation is not linear, then we basically have that Zn minus 1 goes through some nonlinear function f of x to give me Zn, okay? You can do this, you know, instead of the matrix A, or you can have something like that to represent noise, okay? But the bottom line is the relation we have between variables at n minus 1 and n, or between the state and the observations at a given time. They're coupled through some nonlinear function, and so we need to find some way to deal with it. In terms of particles, you know, that's not an issue, right? So when I say we need to find some way to deal with this, can we actually modify the Kalman filter equations to do that? Okay? And the answer, of course, is yes, you can. So, so again, this is the trivial model. So let's say the dynamics are given by this function g, okay, and the observation model by another nonlinear function h, okay. So the methodology basically is called the extended Kalman filter, and it's nothing else but linearization of g and h about the previous state estimates using basically a Taylor series expansion. Okay? And actually there are versions of this where you can use first order Taylor expansion and also second order Taylor expansion. You can do anything you want to. The idea is once you approximate this and you use let's say a Taylor series expansion, it will give you sort of a linear term in zt minus 1 or a linear term in terms of zt, so we'll give you sort of a derivative times zt minus 1, and if you approximate the derivative of the previous state, then the Kalman equation basically follow immediately because the problem will be linear. Okay? So really, it's sort of algebra. There is really nothing there. I think the equations are sort of you linearize and then cut and paste from the old equations to the new equations. But let me show you graphically what the idea here is. So you remember we have y as some function, some nonlinear function g of x, right? So if x is a Gaussian, the idea is when you compute, let's say with Monte Carlo y equals g of x, you don't get a Gaussian, you get a weird distribution as you see here. So this bimodal distribution, okay? So the question is, what do we need to do when we take a Gaussian and we apply this mapping g of x to get a Gaussian, right? So the idea here for this extended Kalman filter is to do linearization in the mode of x, okay? And then basically, all right, so this is the approximation we do, all right? And then we pass the probability, we pass this line through the probability of p of x, and that will give me this dotted Gaussian, which is the extended Kalman filter Gaussian that has a mean basically that is given by this value here. Okay? So how does the linearization look like? So for example, this is the observation model. You write this, first order Taylor series expansion. This is the value. So we had h here, all right? So it's the value h computed at the previous mean, okay? You remember this notation, what is mu of t minus 1? Is the mean of what distribution? Remember, this is the observational time t, right? So what is mu t minus 1? How many data have collected with this? Up to t minus 1. So this is the mean of the one step ahead predictive distribution, okay? So I'm approximating h using that mean, plus the derivative at the same location times the error of this one ahead mean prediction, the error that you do from the observation yt, okay? I don't know why I use y here and not x, but anyways, cutting formulas from here and there give us different equations. So basically, a Taylor series expansion here around the mean of the one step ahead predictive distribution. Okay, so when you look at this, there's absolutely nothing different from what we had before. If you remember the linear model for Kalman filter equations, it was the Gaussian of yt given, let's say, what was the matrix that we had here? It was C times yt plus some constant, so the constant is this, minus this times that, okay? And of course here I'm taking that the noise is Gaussian, okay? If the noise is Gaussian, is not Gaussian, basically you have to incorporate things in a slightly different form, okay? And you do the same thing for the evolution of the dynamics. Let's not bother about U, all right, since we removed it in the previous slides. So basically, you take a linear Taylor series expansion around the previous state, the mean of the previous state, which is mu t minus 1, and this is the error again, times this Jacobian there, that is the gradient of little z with respect to z. Again, once you do this, you look at your generic Kalman filter equations, you cut and paste all formulas, updating that this is your matrix times y, this is the constant, and the rest is basically history. Okay? And depending on, at what location basically, if you do this linearization, you can get various different versions of this extended Kalman filter, including what's called this iterated EKF. If anybody's interested, I can give you to read a very nice book by Sarkar that I promise you can read it in less than 3 hours. Okay, and it has a computer program that comes with it. Has nothing in the context of probabilistic graphical models, but has everything from zero, including applications, to the most complex sort of way for doing some sort of versions of Kalman filter. You can read the book in 3 hours and a minute. So if anybody's interested, I think it's online actually. Okay? And if you don't like his book, you can actually read his thesis that is 2 or 3 years before his book. Okay? And so you can look at those things. All right. And just 6 minutes to finish, right? Another algorithm is the unscented Kalman filter algorithm, UKF. And the idea here is that it is easier to approximate a Gaussian than to approximate a function. So rather than to linearize the function, you try actually to approximate some data to fit a Gaussian. So basically, don't manipulate the function, try to make data to fit in some Gaussian form, okay? And how do you do this? So here's the idea. If, let's say you have a Gaussian, all right? This is the unscented transform basically that you have to use. If you have some distribution that fits in a Gaussian, and you want to pass this through a mapping of the form y equal f of x, right? F is a nonlinear function. What you need to do is you need to compute what is called sigma points, and these are constants basically that you can optimize, all right? These are the columns of the sigma matrix. This is the mean of this p of x. So you calculate the sigma points, and then what you do is you pass these sigma points through the function f, and then you fit this data wise to Gaussian. That's all. So rather than, again, manipulating this function f to give you a linear approximation that will lead to a Gaussian, what you do is you introduce this sigma points, okay? And in this case, I have 2d plus 1 points. You pass this through the function f, and then you fit the Gaussian. So obviously, in our case, we will have to do this twice. We will have to do this for the the dynamical model, and we will have to do this for the observational model. Effectively, if you pass this through the function and you want to compute the mean and the variance, this is the general transforms. Okay, this looks very much like sample mean and sample variance. The only difference here is because these points were selected in some optimal way, their weights would not be equal. So the weights here have to be calculated depending on the parameters that you use in the uncertainty transform. If you try to do this in 1D, in case you get inspired and this reminds you anything, the 3 points, for example, that you're going to use is, if you have a Gaussian in 1D, it's mu minus square root of 3 times sigma, and mu plus square root of 3 times sigma. And the algorithm is, again, sort of, the first step is we need to predict the one header step. So to compute the filtering distribution again, right? You will first have to go one step ahead with observations only up to t minus 1, okay? So to do this, what we will have to do is pass the previous Gaussian distribution, the Gaussian approximation we had for the filtering distribution of ct minus 1. So what you need to do is pass this through the function g that defines the kinematic model, right? That's the dynamical model g. So basically, start with this, define the sigma points, and then pass them through g, and then to compute the mean and the variance of that, you weight them appropriately using the standard formulas for the uncertainty transform, and you get the mean and the variance looking like that. And eventually, you need to compute also this observation model that is non-linear. Okay, so what you need to do is you need to pass the prior of sigma t that we computed on the previous step through the observation model. Okay, so this is what you get. Okay, and eventually you are going to have this is sort of a likelihood, and this is sort of like a prior. So you're going to need to do the filtering distribution. You will need to use Bayes' rule and compute the probability of z given y. So if you have this and you have p of z there, basically just Bayes' rule directly, it can give you the filtering distribution. So this is just from the formulas for Gaussian linear models, right? Nothing specific. This uncertainty UKF algorithm is basically, if you're going to do Kalman filtering, is the desirable algorithm because it has much higher accuracy than the linearization that we discussed before. Okay, and the idea here is you have optimized basically these points. You don't play with the function, and and it's very nice, extremely easy to program. You don't have to program, so you didn't give them any homework to program this, right? But the thing is, maybe you should give them something where they download maybe one of the algorithms and they play with it, or at least you can plot to see how the filtering distribution looks like, how the smoothing distribution looks like, and the like. Just to finish, 145, right? Obviously, these little algorithms are a small part of this whole area of data simulation, right? So if you work with dynamical data, you need to know all of these techniques up and down, every single detail, because playing with data in time requires that you do prediction, you do smoothing, you do filtering, right? All of the above, okay? There are lots of new books that are coming out on data simulation, dressed up with a little bit of mathematics. They don't contain anything new because these ideas have been out there for 20 years, okay? But people who want to write books, I mean, if you want to write a book, you can do something on Kalman filtering in 6 months, okay? And then someone can read it in how many hours? I said in 3 hours, okay? and always there's something to make it different, okay? But in reality, the formulas are in the books already, in papers, and you can read them. And so on Thursday, we're going to change subject and move to variational approximate methods, okay? And there we will need to spend at least 3 or 4 lectures to discuss variational methods, okay? Lots of stuff to read. I'm going to post these lectures today so you guys can take a look and take it from there. All right.